Hi. Hi there. Welcome to Chapter 2. We're going to be studying the chemistry associated with living things. And it's important to understand the chemistry because chemistry is what makes up all living and non-living things on Earth. And all living or everything is composed of matter. Matter is anything that takes up space and has weight. It can be found in three different forms. So I like to think of water when I'm talking about this because water can be found in all three states. As a solid, it is ice. It has a specific shape and volume. As a liquid, it is liquid at room temperature. And it has a volume, but it doesn't have a specific shape. Whatever it's in is going to be its shape. And as a gas, it doesn't have a shape or a volume. And so water as a gas would be like water vapor. So when it gets superheated, it evaporates. All living things are made up of matter. And matter is composed of elements. Elements are the fundamental units, the smallest units. And in general, they cannot be broken into smaller substances. So on Earth, or I won't say that, I'll say, we have discovered over 100 elements, and 94 of the 117 that have been discovered occur on Earth naturally. So let's look at the periodic table so you can see what an element looks like. So here's a periodic table that shows the different elements. It shows the metals and non-metals. I'm not going to go into any of that. We're really going to focus on what makes up an element, and then we'll talk about the most common elements known to life. So an atom is the smallest part of an element that displays the properties of an element. It's made up of three parts: protons, neutrons, and electrons. Protons and neutrons are found in the center of the atom, and it makes up the mass of the atom as well. A mass is just the weight of the structure. Then within the atom, we have charged and uncharged particles. So protons have a positive charge. Neutrons have a neutral charge. They have no charge. Outside of the nucleus, the central portion, is the orbit. And within the orbit, or the orbitals, we have electrons. Electrons have no mass, but they do have a charge. They are negatively charged. And so all atoms naturally are neutral in charge because protons and electrons always equal each other in an atom. So this is carbon up here, and carbon has an atomic mass of 12, has an atomic number of 6. So since only protons and neutrons give the mass, we know if there's 6, the atomic number is the number of protons. We know that there must be 6 neutrons as well because the mass is 12. And then whatever the number of protons is, you're going to have the same amount of electrons. So we also know that in an atom of carbon, we're going to have 6 electrons in the outer orbital. Here we have hydrogen. Hydrogen has 1 proton and 1 electron, no neutrons. Here we have helium, 2 protons, 2 neutrons, and 2 electrons. So it's going to have a mass of 4, but it's going to have an atomic number of 2, and it'll have 2 neutrons. And then here's lithium. It has 3 protons, and it has 3 electrons, and then it has 4 neutrons. The atomic mass is the mass of protons plus neutrons So how many protons and how many neutrons we have. So we have 6 protons, and if the atomic mass is 12, we know that we have to have 6 neutrons as well. So what are the most common elements of living things? The word that we use is chnops, and that makes up carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These make up the majority of the living body, with carbon, hydrogen, oxygen being some of the most common elements. And here's the periodic table. You can find hydrogen's here, carbon's here, nitrogen's here, oxygen's there, phosphorus and sulfur are right here. So we're like all right here, and then we have hydrogen way over here. There is a song that is associated with this slide, and if you click on it, you will probably like it. I tried to play it, but the entire video that I posted was blocked because I tried to play a song. So I will not do that anymore, even though I think songs make the videos a little more exciting. If people are going to block my videos because I played their song, I'm not going to play their song, which makes sense, I think. So what is an isotope then? An isotope is a variation within an atom. So all atoms of a certain type have to have the same number of protons. And if you have a certain number of protons, you have the equal amount of electrons. But neutrons can change. You can keep the same atom with a different mass. And that's an isotope. An isotope is an atom that has a different mass because of the number of neutrons. So here we have 3 forms of hydrogen atoms. Hydrogen in its natural form, in its most common form, has 1 proton, 1 electron. Hydrogen that's associated with heavy water or hard water, which you've heard of, I'm sure, has 1 proton, 1 electron, and 1 neutron, so it's heavier. And then all atoms have a radioactive isotope or a radioisotope that gives off, it's very unstable and gives off radiation as it breaks down to a more stable element. So here we have tritium, which is the radioactive form of hydrogen. 1 proton, 1 electron, and 2 neutrons, so it has a mass of 3. So the mass number is actually an average of the all of the isotopes of any given element. And so with hydrogen, the mass is like 1.001. The most common type of hydrogen is hydrogen with one proton and 1 electron. But they have to take into account for the deuterium and the tritium forms. So there you can see carbon. Carbon has 6 protons, 6 neutrons in its normal form, but its mass is actually 12.011 because we do have carbon 13 and carbon 14. Radioisotopes then are radioactive radioactive versions of the atom. And they're very unstable, and they tend to decompose to a more stable form. And so this gives off radiation as it decays. All atoms have some radioisotope associated with them, and our cells are going to take up regular or radioactive isotopes because we can't distinguish between different types of atoms. And radioisotopes can be potentially dangerous. One thing that I can say, though, is that we all have a small amount of radiation being given off at any given time. We're all a little radioactive. And we can use these radioisotopes to identify tissues, that are mutated. We can use radiation to kill off tissues that have started to grow out of control, like cancer tissues. And so what do we do with this radiation or these radioisotopes? We use radiation to kill damaging cells. We use radiation to kill off spoilage microbes so that our foods can be protected for longer periods of time. The process of killing off spoilage microbes is known as irradiation, and this allows us to keep like peaches, pears, apples, bananas for a long period of time. We use radiation to get rid of damaging cells like cancer cells, to kill off immune system cells that are going hyper crazy in autoimmune disorders. That's another reason we use radiation. And then X radiation is used to look at structures internal the body, so deep, that might have had damage, so that we don't have to just do we don't have to do surgical procedures every time someone breaks a bone. So let's talk about what a molecule is. We know what atoms are. When atoms come together, they form molecules. If you have two atoms of the same type that come together, they form a molecule. If it's two atoms of different types, that molecule is called a compound. So here we see sodium and chlorine. Sodium is a metal. Chlorine in its natural form is a gas, and it's poisonous. But when we put sodium and chlorine together, we produce table salt, which is something that makes our food taste better. And that's a compound. Another compound is water, H2O. So how do these bonds form? If we're going to have hydrogen and hydrogen bond, oxygen and oxygen bond, sodium and chlorine bond, hydrogen and oxygen bond, what's causing the bonding? So a bond is just a relationship between atoms that allows the atoms to be more stable. So remember, in the outer energy, or in the outer orbitals, we have electrons. Electrons like to stay as close as they can to the nucleus, but we have multiple orbitals in an atom. So the first orbital can only contain 2 electrons. If you have 2 electrons in that orbital, they're going to stay right there. Then we have another orbital that contains up to 8 electrons, and a third orbital that contains up to 8 electrons. So anytime we don't have a full orbital, the atom is not happy. It's not as stable. All atoms want their outer shell, so the outermost shell, filled. So we fill from the inner to the outer. So say you have 3 shells. The first shell has 2 electrons and it's full. Second shell has 8 electrons and it's full. And the third shell has 1 electron. It's not full. It wants to either take 7 more electrons in, or it wants to get rid of that 1 electron that it has. So that outermost valence shell is the shell that's going to determine if an atom is going to be interested in bonding at all. So the noble gases have their outermost shell full of electrons. All noble gases are very stable, and they don't like to enter into chemical reactions because they are very stable. So an example, helium is a noble gas. It has 2 electrons in its outer orbital. It only has the first outer orbital. So 2 electrons is all it can fill it, and it's going to be a stable gas. All other atoms that are not noble gases want to be like the noble gases, so they want to also have their outer orbitals full. If we don't have the outer shell, the valence shell, full completely, then we're going to want to enter